Continuing with 4.5a notes, this is second page of the U-Substitution using indefinite integrals. Right, continue with example 4, integral of x cubed square root of 5 minus x to the fourth. We have to go through U-Substitution. We can't just use power rule. There's no way for us to distribute the x cubed through. So first step, I would try and rewrite it using parentheses. Visually, it will help things in terms of identifying your u value. So rewrite square root of 5 minus x to the fourth. That's 5 minus x to the fourth quantity raised to the 1/2. Okay. So we see our u value is simply inside the parentheses, so 5 minus x to the fourth. Okay. Now, this is where we want to begin to look ahead into the problem and see if we have what is necessary in terms of what needs to cancel out. So once you identify your u value, you want to see if you can also identify the appropriate derivative for that u value in the function somewhere. So if you think about power rule, you know that the derivative for x to the fourth will produce some sort of x cubed. So we do have x cubed. So that means that once we find the derivative, this x cubes will eventually or should cancel out. All right, so we want to begin identifying not only the u value, but then looking to see somewhere else in the problem is there a derivative that exists there, which will help cancel things out. Okay, so our u value is 5 minus x to the fourth. Du dx, simply derivative. 5 goes to 0. Negative x to the fourth becomes negative 4x cubed. Cross multiply. Solve for dx, which is du over negative 4x cubed. Okay, so now we make our substitution. X cubed doesn't cancel out yet, so we leave that value there. 5 minus x to the fourth, we do have the u value for that, so u to the 1/2. Dx gets replaced with du over negative 4x cubed. The x cubed cancel out, but the negative 4 stays, so we have to make sure we keep track of that. I'm going to pull that out in front of the indefinite integral. So we're simply having to find the indefinite integral, the antiderivative for u to the 1/2. So we go through power rule, u to the 3/2 over 3/2. We add 1, right? We can resolve the complex fraction by bringing the 3/2 up as 2/3. So negative 2/12 reduces to be negative 1/6. And then finally, we're going to replace our u value back in terms of x. So negative 1/6, 5 minus x to the fourth raised to the 3/2 plus c. Or you can write it as a radical. So negative 1/6 square root of 5 minus x to the fourth cubed plus c. Okay. Example 5. Integral of tangent x to the fifth plus secant squared x. Again, I'd like to rewrite it using parentheses. It'll help us kind of piece together the u value a little bit easier. So I'm going to rewrite this as tangent of x raised to the fifth, secant of x raised to the second. Now we have two choices. Maybe our u value is tangent of x. Maybe our u value is secant x. So it helps to kind of look ahead, right? If, let's say, our u value is tangent, right, then our derivative will be secant squared, which is exactly what we have here, which we will be able to cancel out. Okay. Now, if our u value is secant x, then our derivative will produce secant tangent, which will not be enough to cancel all this out. All right, so we want u value to be tangent x. So our derivative is simply going to be du over dx, so tangent becomes secant squared. Cross multiply, we get dx equals du over secant squared x. So we make our substitutions. Tangent x gets replaced with u to the fifth. Secant squared x stays. And then dx gets replaced with du over secant squared x. Okay. Cancel out nicely. We're simply left with integral of u to the fifth. So the power rule gives us u to the 6th over 6 plus c. And then finally replace our u value in terms of our original x value, which is tangent x. All right, example 6. This is a different method for U-substitution. This is called the change of variable U-substitution method. And this is where halfway through we're going to see that we will be unable to cancel out with the variable sitting here. So let's say we step through this problem the same way that we did with previous. So convert radicals to rational exponents. We see parentheses here, so we set u equals to x plus 3. Okay, derivative, d over dx is 1, so solve for dx equals du. Make our substitutions, so x plus 3 gets replaced with u to the 1/2. X does not get replaced, but dx does get replaced with du. And so now we have a problem here, because this x does not cancel out. However, we can work around this issue by replacing x in terms of u. And so we want to look to see what's given to us and what we can do to help us work around this problem. So we do have this u equals x plus 3, right? What if we rearrange this to solve for x? So x is u minus 3. If I do that, then I can replace this x in terms of u. In this case, u minus 3 times u to the 1/2 du. Okay. So now we have everything in terms of u. So we have to decide what's our next step, right? Maybe we want to use power rule. And if we want to use power rule, then we have to expand, right? We can't have any parentheses with multiplication with multiple terms of u. So distribute the u to the 1/2 through to expand. And if I'm multiplying bases, I'm going to end up adding exponents. So this is u to the first power, u to the 1/2. So 1 plus 1/2 is 3/2. Distribute the 3 times u to the 1/2, which is negative 3 u to the 1/2. So we go through power rule, add 1, so u to the 5/2 over 5/2. U to the 1/2 becomes u to the 3/2 over 3/2. Okay. Resolve the complex fraction, bring the 2/5 up, bring the 2/3 up. The 3's cancel out. So we have our solution replacing the u in terms of x. So we can either write it as x plus 3 to the 5/2, x plus 3 to the 3/2, or we can write it as radical form.